Hello, everybody. All right, this is going to be the second video, all right, in getting some training using SPSS. Those of you guys who, have decided that SPSS is just not for you this semester, luckily you get that option this semester. I would recommend, though, continuing to watch this video, working through this worksheet, because, yeah, it does it in SPSS, but even outside of the SPSS, it helps with figuring out what sorts of questions get addressed with each of the types of statistical analyses that we learned about, and how do I interpret the results of those statistical analyses. All right, so you guys don't have to do the statistical analyses. I'm going to do that for you, but you do still have to interpret the results. All right, so I'm going to send you guys all of the results and all of the test statistics and the p-values and the descriptive statistics, and you guys are going to have to interpret those results when you write your paper, right? And so understanding how to interpret those numbers and write them into a result in plain English, all right, will be helpful before you write your final paper. All right, so what I have up here on the screen, I have the SPSS file that has the work in it that we did in the previous video where I just introduced you guys to what SPSS looks like. We changed some variable names. We told SPSS what our nominal variables mean. All right, remember that's what's happening here in these cells. And over here, I have on the document camera, hello everybody, I have the actual worksheet. All right, so I'm going to be filling in answers so that you guys, so we make sure that everybody has the correct answers filled in on their worksheets, and so that we can make sure sometimes I'll write what I would have written on the board here on this piece of paper. All right, so we are going to start with number 3 on the worksheet. Here's where we are. We did numbers 1 and 2 before. I don't have the answers to number 1 written in here, but we are going to start with number 3, which is getting some descriptive statistics in SPSS. So let me try to get some more of this worksheet showing at one time. All right, so 3A asks, what proportion of our sample is male and female? All right, remember these descriptive statistics are telling us only about the people in our sample. All right, and so this is why it explicitly says what proportion of our sample is male. All right, it's not asking us to estimate what proportion of our population is male based on what we learned from our sample. That would be the inferential statistics. Here, we're just talking descriptives. What did our sample say to us, right? The 205 people who answered this survey. Yeah, 205. All right, so to get a proportion, we are going to go to Analyze, Descriptive Statistics, Frequencies. All right, within this menu, we are going to move over the variable that we're interested in, all right, which in this case is gender. And down here, hopefully you guys can see my mouse moving, automatically in this menu, Display Frequency Tables is checked. Remember when we talked in the PowerPoint slides about one-way frequency tables, we said that in that table, it's going to provide the raw count information. So how many people circled, the number of people, circled male and circled female. And it's also going to convert that to a proportion of our sample. All right, so as long as this box, Display Frequency Tables, is checked, we'll get that information. And we click OK. All right, and here on our output screen, we can see that 68 out of 205 people in the sample circled male, and that's 33.2%. All right, so I'm going to write 33.2% of our sample is male, and 66.8% of our sample is female. All right, so 2/3 of this sample is female and 1/3 is male. All right, the next thing that we want to learn is what proportion of the sample has, no IBM, what proportion of the sample has a tattoo. All right, and the way that we do that is we go back to Analyze, Descriptive Statistics, Frequencies. We're no longer interested in gender. Now we're interested in what proportion have a tattoo. So we're going to move have a tattoo over to the variable box. Display Frequency Tables is still checked, so we click OK. All right, and here we see that 84.9% of the sample does not have a tattoo, and 15.1% of the sample does have a tattoo. All right, for those of you guys who are doing this in SPSS, all right, working along with me in SPSS, please feel free to pause the video, all right, as you're doing these analyses in SPSS, and then start the video again to compare your answer to my answer. I'm going to be going through this quicker, hopefully, in the video than I am in class, than I would have in class, because in class there would have been a lot of pauses to make sure that everyone was on the same page and no one was getting left behind. But in the video, I'm just going to work through it, all right, so that you can pause and continue playing when you're ready. Okay, the next question asks us, what proportion of the sample makes friends more easily with opposite gender, same gender, equally well with both genders? We're going to go back to analyze, descriptive statistics. Why aren't you clicking? Analyze, descriptive statistics, frequencies. We're no longer interested in tattoos. Now we're interested in the results of this friends variable. So we're going to move friends over. Display frequency tables is checked. We click OK. All right, here we see 35.6% of people said they make friends more easily with the opposite gender. 14.1% said they make friends more easily with the same gender. And about half of people, 50.2%, said they make friends with everyone. It doesn't matter what their gender is. One thing I want to point out here that, I don't know, you may come across one day, all right, people who are learning SPSS, we have these two columns here, percent and valid percent. In our data set, these two columns are the same because we have no missing data. Everyone answered all 205 questions. Sometimes though, and we can see here, nobody skipped this question because it says 0 next to missing. Sometimes though, in a data set, you'll have instances where only a subset of your sample answers a question. All right, for example, in our survey, we ask people, do you have a valid prescription for ADHD medication? And some proportion is going to say yes, and some proportion is going to say no. And the ones that say yes will then see a further question asking them about how often they take it, or you know, which specific drug they're prescribed. And so when we look to see maybe which drug is getting prescribed the most often, we will see a line down here that says missing, and all of the people who do not have a prescription, all right, they couldn't even see this question on the survey because they don't have a valid prescription. We'll see the count of people who skipped the question. And then in the percent column, we'll see some proportion of people who didn't see the question. And in the valid percent column, those people get ignored. All right, so in the valid percent column, it will show the percentage of the people who saw that question who gave each possible response option. All right, so percent gives you how many people chose each option and how many people missed the question, and those will add up to 100. Valid percent ignores anyone who skipped the question and shows only among the people who actually answered this question what proportion gave each possible option. Here, those two columns are the same because we have no missing data. Okay? All right, on the worksheet, we move from proportions to means. All right, so our descriptive statistic for these continuous variables, we want to know on average, how many ear piercings did this sample have? How many CDs did they own? What was their actual height? What was their desired height, etc. To get those means, we're going to go to analyze, descriptive statistics, frequencies again. Here, we are first interested in how many ear piercings they have. If we just clicked OK right now, we would not get a mean. We would get a frequency table that said what proportion chose 0, what proportion said 1, 2, 3, etc. To get the mean, we're going to click where it says statistics and check the box that says mean. All right, you can see there's lots of other options in here. If we wanted the median, if we wanted standard deviation or variance, etc. You could ask for lots of different descriptive statistics in here, but we're just interested in the mean, so that's what we're going to check. Press continue. I'm going to uncheck this frequency table box because I'm not interested in knowing the proportions. I only want to know the mean. All right, on average, how many ear piercings do people have? I'm going to click OK. All right, so here we see 205 people answered this question. Nobody skipped it. And the mean number of ear piercings is 2.76 piercings. All right, we're going to do this again for number of CDs owned. And here's where you will see the 90s-ness of this data set. All right, we're going to go to analyze, descriptive statistics, frequencies. We're going to put in number of CDs. All right, mean is already going to be checked in here because SPSS remembers what we just did. All right, and we are going to click OK and see that the mean number of CDs owned by this data set is 72.84 CDs. All right, and I'm sure to you guys that sounds like a lot of CDs, and I will not admit out loud how many CDs I have in a box, all right, in my office, my home office. Okay, it's a lot more than 72. Okay, the next thing that we want to know is the mean of actual height and desired height. And here I want to show you guys that when we ask for things, this variables box is large. All right, so we don't have to ask for things one at a time. To save ourselves some time, if we want the same analysis done on multiple variables, then we can enter multiple variables in this box. All right, so we want to know the mean of actual height, the mean of desired height, and the mean of this importance of looks versus personality variable. So we can enter all three of those variables into the variables box. It's going to give us the mean of all three of those variables. We press OK. Our output here looks a little bit different because now instead of just seeing one table, all right, for number of CDs, we see a table with multiple columns, each column having the mean data for these variables. All right, and so we can see that the mean of actual height is 67.03 inches. So people on average are about 5'7". The mean of desired height is 68.37 inches. So on average, they'd like to be about 5'8 1/3. And the mean of this looks versus personality variable is 4.54. All right, so we see that right there on the paper. All right, so these are our descriptive statistics. All right, in the descriptive statistics lecture, we talked about other things like the median, the mode, variance. You could ask for all of those things inside that menu that we just used. This worksheet just asks us to find proportions and means. All right, and so that's what we focused on. And now that we are familiarized with our data set, we are going to jump into making some population inferences. All right, what do we think is true of all Penn State students based on what this sample of Penn State students has told us? All right, and so first we're going to start with this tattoo variable. All right, so we're going to learn some things, make some inferences about tattoo ownership at Penn State. All right, so this first question says, 16% of people in the United States had a tattoo in the same year our survey was administered. Is the distribution of tattoo ownership at Penn State the same as the US distribution? All right, so what this question is asking you to do is it's asking you to calculate what is the proportion of students at Penn State who have a tattoo, and then ask, is that proportion equal to some external reference point? All right, so we got this data from a different survey. Some other study was done and found that 16% of the people in the US had a tattoo. All right, and so we want to know if our sample suggests that the population at Penn State is equal or not equal, right, to this external reference point. All right, and so what we're doing, sorry, this is getting sideways, but what we're doing is there were two possible answers to this question of having a tattoo. We have data from our sample, and we have data from the US, all right, which came from some other survey. I don't even remember where I got that number from, but some other survey did this and found this answer. All right, and so we want to know in our sample, if we look back up here at the descriptive statistics, we found that 15.1% of the sample has a tattoo, which means that 84.9% of the sample did not. And in the US population, 16% of people had a tattoo and 84% of people did not. All right, this is our expected distribution. If Penn State were just like the general US population in terms of tattoo ownership, then we would expect that at Penn State, 16% of students would have a tattoo and 84% would not. We have some data from our sample, some evidence about how many people at Penn State have tattoos. And what we want to know is, does this evidence suggest that the population is the same as the US distribution, or does it suggest that it's different? All right, so when we do this chi-square goodness of fit test, our null hypothesis is that what we observed is equal to what we expected. All right, so in other words, Penn State is equal to the US when it comes to tattoo ownership. And the alternative is that what we observed is not equal to what we expected, which means that Penn State is not equal to the US in terms of tattoo ownership, meaning that we could find that Penn State students are less likely. The question is, 15.1 is less than 16. The question is, how strong is that evidence? Is it strong enough for us to conclude that at the population level, we think Penn State students are less likely to have tattoos? Or is this weak evidence that we think is just a result of chance and sampling error. All right, so we have our null and our alternative hypothesis. We're going to find out which one is supported, more supported, by doing this chi-square goodness of fit test. Remember, the chi-square goodness of fit test is the one that's buried down in the menus. So we're going to go to Analyze, Non-Parametric Tests, Legacy Dialogues, chi-square. All right, the test variable that we're interested in is how many people have a tattoo. All right, and in our expected values, the default is expecting a 50-50 distribution here. That is not what we expect. So we have to click on values. And remember, when we enter these values, we have to enter them in the order that the variable was coded. All right, so tattoo is coded 0 equals no, 1 equals yes. 0 is the lowest code. All right, so we're going to enter what we expect as far as zeros go, which is 84%. And then we're going to enter what we expect as far as yeses, which is 16%. All right, so we expect 84% of our sample to circle 0 and 16% of our sample to circle 1. All right, so we're going to enter things in this order. We're going to click OK. All right, so when we look at our results, SPSS, what's the word that I want? They don't show proportions. All right, so they convert that proportion from a proportion to a count. All right, so the 15.1% saying yes reflects that 31 out of 205 people in the sample said yes. And if Penn State were just like the US, we would have expected 16% of them, or 32.8 people in the sample, to have said yes. All right, and so 31 is very close to 32.8, so I think we can guess what the result of this test is going to be. But if we look down here, the important pieces of information, what you will get when I give you the results from the data analysis on your survey, you'll see that chi-square equals 0.118 and p equals 0.732. All right, on this sheet of paper over here, I'll keep this written down. If p is less than 0.05, we are going to reject the null hypothesis. All right, and if p is greater than 0.05, we are going to fail to reject the null hypothesis. All right, with a p-value of 0.732, all right, the 0.732 that we have here on the screen, are we going to reject or fail to reject that null hypothesis? We're going to fail to reject. All right, 0.732 is much bigger than 0.05. Because we failed to reject the null, that means that we side in favor of the null. And the question is, what does that mean in plain English? All right, what are we inferring about the population based on this result? And what I hope that, that I can train you guys to do is to just read what the null hypothesis says. All right, so we're siding in favor of the null hypothesis, and what that means is that what we observed is equal to what we expected. All right, and so we think at Penn State, the distribution of tattoo ownership is the same as the US distribution, all right, which is option number 1 on this worksheet. All right, so people at Penn State have tattoos in the same proportion as the general US population. All right, that's what we've learned from this chi-square goodness of fit test. We had some information from our sample, we did the test, now we can use that information from our sample to make an inference about the population. All right, based on what my sample told me, now I think at the population level that Penn State students generally are just as likely as the general US population to have a tattoo. Okay, next question. We're going to add in an additional piece here. Is there a gender difference in the likelihood of having a tattoo? All right, so I didn't, excuse me, I didn't bring my table of appropriate statistical tests here today. Maybe I can draw one up real fast. All right, do we have a predictor or not? Categorical, continuous, no predictor. All right, what's my outcome? Categorical, continuous with 1 or 2 outcomes. All right, what we just did was a chi-square goodness of fit test. All right, there was no predictor. We did not use a variable from our sample to divide our sample into groups prior to the analysis. We looked at the data from everyone in our sample and compared that to an external reference point, all right, which in this case was the US population. Here in this question, is there a gender difference in the likelihood of having a tattoo? This is asking us to use this gender variable from our survey to divide our sample into two groups, men and women. All right, so we do have a predictor. We're using a variable from our sample to divide our sample into groups. And that predictor is a categorical variable. Oh, I messed my table up. I'm sorry. Okay, just ignore the last minutes of video. Sorry, guys. No predictor should be the first. That's where I was getting myself confused. Okay, so in the last example about tattoo ownership, we had no predictor. We were not dividing our sample into groups at all, and we did a chi-square goodness of fit. In this example, we do have a predictor, right? It's gender, which is a categorical predictor. And the thing about these genders that we're interested in is whether or not they have a tattoo, right? Which is answered yes or no. So that's a categorical outcome. And when we have a categorical predictor and a categorical outcome, we do a chi-square test of independence. All right, so that's written in kind of small. Let me write this p-value stuff at the top that we're going to need in a minute. Okay, so we are going to do a chi-square test of independence to find out if there is a gender difference in the likelihood of having a tattoo. All right, so in other words, this on the data analysis plan, this could be framed something like, are men more likely to have tattoos than women? All right, so are the men's answers on this tattoo question different from the women's answers on this tattoo question? To do our chi-square test of independence, we have to start with the crosstab table. All right, and I have the crosstab table printed here for us to fill in on the worksheet. Remember, in this crosstab table, we're going to put our predictor variable, which is gender, into the columns box, and our outcome variable, which is whether or not these genders have a tattoo, into the rows box. If I clicked OK, I would just get the crosstab table. All right, in order to get the chi-square statistic, finding out if the men's answers are different from the women's answers, I need to click where it says statistics and select the box that says chi-square. All right, and press continue, and then OK. All right, so let's look first at our crosstab table. SPSS prints out the crosstab table within this test as counts instead of proportions. And when you are looking at the results of a chi-square test, it is important that you always convert those counts into proportions. All right, the reason why. If we look at these counts, looking at the raw counts suggests that women are more likely to get a tattoo than men. All right, because we have 18 women in our sample with a tattoo and 13 men in our sample with a tattoo. All right, what's the problem though? All right, why are we seeing such a large number for women that has nothing to do with the actual likelihood that women have tattoos or not? All right, and the issue, hopefully this is like Blue's Clues and you guys are all yelling the answer at home, but the issue is that there are twice as many women in the sample as there are men. All right, so if men and women were equally likely to get tattoos, we would see a number twice as large for the women as for the men, simply because there are twice as many women in the sample. All right, and so it's important for us to convert these counts into proportions. The way that we are going to convert this into proportions is we're going to take the number inside the table, all right, so 55 out of the number at the bottom of the column. All right, so 55 out of 68 men do not have a tattoo, which is equal to 80.88%. All right, do not have a tattoo. And 13 out of 68 men do have a tattoo, which is equal to 19.12%. All right, and we can do the same thing for women. 119 out of 137 women do not have a tattoo, all right, which is 86.86%. And 18 out of 137 women do have a tattoo, which is 13.14%. All right, so when we look at the raw counts mislead us into thinking that more women have a tattoo. The problem is that we see a larger number for women here because there were just more women in the sample. When we convert this to proportions, we see that 19% of the men in the sample have a tattoo, while only 13% of the women have a tattoo. All right, so in our sample, within the sample, the men are more likely to have a tattoo. The question is this evidence provided by our sample strong enough to suggest that at the population level, the men at Penn State really are more likely to have a tattoo? To make that inference, we have to look down here at our chi-square statistic and our p-value. Remember here, we're looking at the top row where it says piercing chi-square. All right, and so our chi-square statistic is 1.266, and our p-value is 0.261. With a p-value of 0.261, are we going to reject or fail to reject the null hypothesis? All right, we're going to fail to reject the null. Sorry, I didn't even write the null and alternative here. Don't worry, that's the same as class. I would have also forgotten to write this if we were in class. For this test, the null hypothesis is that the men are equal to the women, all right, when it comes to tattoo ownership. The alternative hypothesis is that men and women are not equal when it comes to tattoo ownership. All right, and so here we fail to reject the null, which means we side in favor of the null hypothesis. And in plain English, we conclude what that null hypothesis says, right? Which is when it comes to having tattoos, men and women are equal, right? Or right here, men and women are equally likely to have tattoos, right? That's our appropriate conclusion for this test. Okay? Chi-square test of independence. We divide our sample into 2 or more groups based on their answers to a question from our survey, in this case, gender. And then once we have those people divided into groups, we look to see if their pattern of responses on another categorical measure are the same or different. All right, so is this pattern of yeses and nos for the men the same as this pattern of yeses and nos for the women? This test concludes yes. While there are some differences in the sample, we think those differences can be explained, are likely to be explained by chance and sampling error. And so as a result, we fail to reject the null, and we conclude that at the population level, we think that at Penn State, men and women are equally likely to have tattoos. Okay, moving on to number 5. All right, let's decode what kind of test we need to do here. This question is asking, do women have more ear piercings than men? All right, so our first question that we have to ask ourselves is, does this ask us to divide our sample into groups? All right, and if we look at the question, yes, we have 2 groups, men versus women, which means that we're going to divide our sample into groups based on their gender, all right, which is a categorical predictor. All right, so we don't have any tests here or here. All right, so we have only 2 options here. It's either going to be chi-square test of independence or this mystery test that we haven't written in yet. And the second thing is, once we have these people divided into groups, what is it that the people in these groups are doing that we're interested in? And they are having ear piercings. All right, if we look back at the survey, the way that this was measured, it asked, how many ear piercings do you have in total? And people wrote in a number of piercings they have. All right, this is a ratio response measure, which gives us continuous data. And when we have a categorical predictor and a continuous outcome, we do an independent samples t-test. All right, so what this independent samples t-test is going to do is it's going to ask, is the mean number of ear piercings the same for men and women? All right, so at the population level, on average, do men and women have the same number of ear piercings? Or do I think that at the population level, men and women do not have the same number of ear piercings? All right, so one group has more ear piercings than the other. Someone in class would say, this question wanted to know, do women have more ear piercings than men? Why don't we write the alternative hypothesis as men less than women? I write the questions on the worksheet and on the data analysis plan the way that regular English language would ask the question, all right? Because in the real world, that's what you would see, all right? Someone at your office or, you know, your boss would say, well, can you figure out, and then they would ask you some question in regular English, and you would have to convert that into, you know, math sort of language to understand what's happening. When we write the null and alternative hypotheses, you can write them in what's called a directional or non-directional format. We are using the non-directional format, just not equal to and not specifying the direction of the difference, just to simplify things. All right, so just for our purposes in class, we're always just going to write equals or not equals. All right, and because if women have more ear piercings than men, that means the men and women are not equal. All right, the question specifies the direction of that inequality, but we are just in our alternative hypothesis going to write that they are not equal. All right, so we're going to do this independent samples t-test to find out, based on the evidence from our sample, does that evidence suggest that at the population level, on average, men and women have the same number of ear piercings, or does it suggest that on average, the number of ear piercings for men and women differ? To do this independent samples t-test, we're going to go to Analyze, Compare Means, Independent Samples t-test. All right, remember that these paths are on the bottom half of that handout that has the table of appropriate statistical tests at the top. All right, so I'm going through this a little quickly. I know in the SPSS guidebook that's posted on Blackboard, it also tells you these paths to follow. All right, in the independent samples t-test menu, we have to specify the variable whose means we're comparing and the variable that we're using to divide people into groups. All right, so the variable that we're using to divide people into groups is gender. We have to tell SPSS how gender was coded, right? And our code book, that's on the first page of this worksheet, tells us that gender is coded 0 for male and 1 for female, right? So we're going to put in, we're going to compare the males and the females and press continue. And the thing that these males and females are doing that we're interested in, whose means we're interested in, is how many ear piercings they have. All right, so we're going to put number of ear piercings into the test variable box, and then we're going to click OK. All right, when this result prints out, first we'll look up in this top box where it says group statistics. That's the descriptive statistics. All right, again, we see there are 68 men in the sample and 137. Among those 68 men, they average in the sample 0.54 ear piercings, all right, which tells us that about half of the sample has 1 ear piercing. You have to remember, this is the 90s. That was popular in the 90s for guys to have 1 ear pierced. And the women in the sample have, on average, 3.86 ear piercings. All right, and so now what the t-test is going to do is it's going to say, okay, in the sample has provided some evidence of a difference. The question is, how strong is that evidence? Is that evidence strong enough to convince us that at the population level, there probably really is a difference between men and women in terms of their number of ear piercings? All right, we have to look for our t-statistic and our p-value. Remember, we are not looking at this test. We are looking for a t-statistic, and this is an F. All right, so we don't want that. We're going to scroll right past that to look for our t-statistic on the top line of data. Our t-statistic is negative 12.015. All right, remember that it's negative because the smaller mean came first. So this test asks, is 0.54 minus 3.86 different from 0? And because 0.54 came first, this is a negative number. And so it's asking, is this negative number different from 0? And as a result, we get a negative t-statistic. And our p-value is 0.000. All right, remember, this does not mean that p is 0. P can never be 0. It just means that the p-value is so small that when they round to 3 digits, the first 3 digits are 0. All right, so we have this p-value of 0.00. Here's our decision rules up here at the top. All right, when p is less than 0.05, all right, which we certainly have here, we are going to reject the null. All right, so we have evidence now to suggest that the null is not supported, which means that we are going to side in favor of the alternative hypothesis, all right, that at the population level, men and women are different. All right, and what we should do when we conclude that men and women are different, because if you wrote that into your paper, men and women differ in terms of how many ear piercings they have, your reader is going to wonder, well, I wonder which group had more ear piercings. So we can look at our means here to decide which group had more. All right, and so the group that had more obviously, is that women have more ear piercings than men, and this is our appropriate conclusion. All right, so in your paper, you would write, women at Penn State have more ear piercings than men. All right, next question. Do people with tattoos have more ear piercings than people without tattoos? To figure out what kind of test we do, the first thing we need to ask ourselves is, does this question ask us to divide our sample into groups? All right, and so this is saying, do people with tattoos have more ear piercings than people without tattoos? All right, so this is how we're going to divide our sample into those with and those without tattoos. That's a categorical predictor. So that means that one of these two tests has to be what we're doing. These are the only tests that we're learning about to do when we have a categorical predictor. So it's going to be one of these tests. And so we need to know, what is it about these people with and without tattoos that we're interested in? And what we're interested in is how many ear piercings they have, right? Which we just saw as a continuous variable. It was measured on a ratio response scale. All right, so when you have a categorical predictor and a continuous outcome, we're going to do an independent samples t-test. This independent samples t-test is going to ask, do people with tattoos have the same mean ear piercings as people without tattoos? All right, so I'll write NT, no tattoos. All right, are these two groups of people the same when it comes to having ear piercings? Or are these two people different? All right, when it comes to how many ear piercings they have? Is the mean number of tattoos among people with tattoos different from the mean number of ear piercings among people without tattoos? All right, we have this question in regular English, and we convert it to this set of statistical hypotheses. All right, this is the decoding that you guys need to do when you're working on that data analysis plan. All right, so in order to test this, is the mean of these two groups equal, or are the means different? We're going to do an independent samples t-test. All right, so we're going to go back to analyze, compare means, independent samples t-test. We are still interested in the number of ear piercings, but we're no longer interested in using gender to divide our sample into groups. Now we're interested in dividing them based on whether or not they have a tattoo. If we look back at our code book, we see that tattoo is coded 0 equals no, 1 equals yes. So when we define groups, we can leave the 0 and the 1 there. We'll press continue and then OK. All right, let's look first at our descriptive statistics. Within our sample, the people who do have a tattoo, all right, so we have X bar tattoos here, all right, the sample mean for people with tattoos is 3.94, and the sample mean for people without tattoos is 2.55. All right, so our sample suggests that maybe at the population level there is a difference, and people with tattoos have more ear piercings than people without. We have to find out if that difference is statistically significant, all right? If it's likely to be due just to chance and error or not. All right, we scroll over to our T statistic right here. We see that T is equal to -2.978, and our p-value is 0.003. All right, let's look back at our decision rules. With a p-value of 0.003, would we reject or fail to reject the null hypothesis? Need some Jeopardy music. All right, we would reject. All right, 0.003 is less than 0.05. All right, so we are going to reject this null hypothesis. We are going to side in favor of the alternative. All right, and in order to figure out what we're going to write in plain English, we need to just read this math sentence. The mean number of people with tattoos is not equal to the mean number of people with no tattoos. All right, and specifically, the way that they differ is that people with tattoos have more ear piercings than people without tattoos. All right, and so we conclude people with tattoos have more ear piercings than people without tattoos. That is our conclusion in plain English that would go into our final paper. Okay? If you have questions about any of these things as we're going through the video, pause the video, leave a comment on the video. I will come back and answer the question that's in your comment. All right, I think that YouTube is giving me notifications of these questions. All right, and so I will go back and answer the question that you've left in the comments. Okay, moving on to number 6. We're leaving ear piercings, and now we're going to start some investigation into what we have learned about height. All right, and so the first question asks, are men taller than women? All right, so decoding this sentence, figuring out what kind of test we need to do here. Does this question ask us to divide our sample into groups? All right, we have two groups here, men and women. That's something that was measured in our survey. We have that gender variable. All right, so that means that we have a categorical predictor. And the thing about these men and women that we're interested in is how tall they are. All right, and this was measured by writing in your height, so that's a ratio variable, gives us continuous data. So again, we have a categorical predictor and a continuous outcome. So we're going to do an independent samples t-test. All right, this is a popular test. We do these a lot. All right, so let's convert this into statistical language, our null and alternative hypothesis. With an independent samples t-test, the null is always. All right, so you've seen me write this a bunch of times. How this is written doesn't really come from the writing of the question. It comes from this test does something specific, and it always does the same thing. What the test does is it asks, is the mean of group 1, which in this case is men, equal to the mean of group 2, which in this case is women? All right, so are those two means the same at the population level, or are they different? All right, and you can find those general hypothesis formats on the second page of the table of appropriate statistical tests. All right, and it'll say mean of group 1 equals mean of group 2, and you just plug in what your group 1 and group 2 are, in this case, men and women. All right, so we want to know if the mean height of men at the population level, that's what mu is, the population mean, is the population mean height for men equal to the population mean height for women, or are they different? And to find out, we have to do an independent samples t-test. All right, so we're going to go back to analyze, compare means, independent samples t-test. We are no longer interested in number of ear piercings. The thing whose mean we want to calculate now is actual height, how tall people are. And we don't care about people with and without tattoos. We care about gender, all right, which recall was coded 0 and 1 for males and females. So we'll leave those 0s and 1s in the grouping, press continue, and press OK. All right, let's look first at our descriptive statistics. In the sample, all right, that's what this X bar is, the sample mean. In our sample, the men are on average 71.09 inches tall, all right, so they're almost 6 feet, they're 5'11", and the women on average are 65.01 inches tall, all right, they're 5'5" on average. Is that right? Yeah, 5'11" and 5'5". So the sample has provided some evidence to suggest that men are taller than women. The question is that evidence strong enough to suggest that it holds at the population level, that men, we think at the population level, men are taller than women? So we scroll over here to look for our t-statistic and our p-value, all right? Because there was a big difference between the men and the women in the sample, we see a big t-statistic, all right? Remember that t-statistic summarizes the magnitude of the difference between the means of these two groups in the sample. So because we saw a big mean difference here, we see a big t-statistic of 16.416. And because our t-statistic is big, we get a small p-value. Remember, the p-value tells us what are the odds that we found a difference that large in the sample due just to chance or sampling error. This is a big difference, all right, 6 inches. So it's unlikely that we found that just due to chance and sampling error. It's unlikely that we just got a weird sample that happened to have all the tall men from the population and all the short women from the population. All right, and so the odds of this being due to chance and error are very low. And so because of that, because p is less than 0.05, we are going to reject the null. And we're going to conclude, all right, remember we're just reading what this says. The population mean for men is not equal to the population mean for women. And specifically, the way it differs is that the men are taller than the women. All right, and so that's what we conclude in plain English. Men are taller than women, at Penn State anyway, because that's where our data is coming from. Okay, let's turn the page. All right, we're gonna think logically over here to help us learn about what something that's going on over here. We're also going to learn how to do something new in SPSS. All right, so B says there are 2 ways to determine if people want to be taller on average. All right, remember that we have these 2 variables on the survey. How tall are you in inches? And if you could be any height, how tall would you be in inches? So we have these 2 variables in our data set, actual height and desired height. And so what we can do is we can create a new variable to see if there is a difference between people's actual height and their desired height. And so we're going to create this new variable that is equal to desired height minus actual height. All right. If people want to be taller, what would that imply about the result of this equation? So if a single person in our data set wanted to be taller, then their desired height would be a number larger than their actual height because they wish they were taller. So this would be a bigger number than this. So this tells us that if the answer to this equation is a positive number, people want to be taller, right? And conversely, if people wish they were shorter, then their desired height would be a smaller number than their actual height. And so when we subtract smaller number minus larger number, we would get a negative answer. And that would tell us that people wish that they were shorter. Right? And in the middle here, if people's desired height is exactly equal to their actual height, they don't wish to change their height, they're perfectly satisfied, then we would get 0, because we would have their desired height is the same as their actual height, so that one number minus itself is 0, and this means that people wish that they would have no change to their height, right? They're perfectly satisfied with their height. So what we're going to do first is we're going to compute this new variable, so we can see how to do something new in SPSS. To compute this new variable, we're going to go to a new menu, Transform, and the first option is Compute Variable. All right, and so this is a new kind of menu, one that we haven't seen before. What this is asking us to do, essentially, all right, if we ignore everything that's happening here and just look at the basics, we're going to make a new variable, which they call the target variable, and we're going to say this new variable equals some math expression that I write over here. All right, so we're going to call our target variable height change. You could call it anything you want, all right? You can copy me, you can call it something else if you want. The only thing is you cannot have a space and you can't put any weird, like don't use an asterisk or, anything like that. So just height change with no space. SPSS does not like spaces in the variable names for some reason. So we have height change is equal to desired height, right, height choice, minus actual height, right? Desired height minus actual height. In our variables, it's called height choice minus actual height. So what this is going to do, for each person in our data set, SPSS is going to take their answer to the height choice variable, subtract away their answer to the height variable, and put that answer into a new column labeled height change, right? And we press OK. Now, the output doesn't really show us anything has happened here. It just shows us that we have asked SPSS to compute this new variable and that SPSS has done it. But if we go back to our data set and scroll all the way to the right, here we see this new variable, height change. All right, so here we see for person number 1, their height and desired height are the same. And so as a result, their height change variable is 0. All right, and so we see this person wants to be 2 inches shorter, this person wants to be 4 inches taller. This person wants to be 8 inches taller. Let's see how tall they really are. They're 5'8" and they want to be 6'4". That's okay. I don't know. Somebody wants to be really tall there. All right, but we have this whole column of all of these numbers of how much people would change their height in an ideal world. All right, and so what we want to know now, our question over here is, do people want to be taller? All right, and so if people wanted to be taller, then the mean of this new variable that we've created would have to be a positive number. All right, and so what we're doing here, if we look at this question, is the mean greater than 0? Do people want to be taller? All right, let me write this up here because I didn't write it the same way on the worksheet. Do people wish they were taller? Does this question ask us to divide our sample into groups? It does not. All right, so we just have do people, all the people, not groups of people, just all of them. All right, so we have no predictor over here. So we have to do one of the 3 tests that are going to show up over here. And what is it about the people that we're interested in? All right, what we're interested in is whether or not they want to be taller. All right, and we learned over here that if they were taller, if they wanted to be taller, their answer would be a positive number. And if they wanted no change, their answer would be 0. And we're interested in the mean of this new variable that we've created. So we're interested in knowing, is the mean of that new variable equal to some specific number? All right, and so we have no predictor and a continuous outcome, the mean of this new variable. And here we do a one-way t-test. All right, and so in this one-way t-test, we're going to ask, is the mean equal to 0, meaning that people want no change in their height? Or remember that the null hypothesis is always no difference. So here the hypothesis is people want no change in their height. Their mean is 0. All right, and the alternative is that this mean is not equal to 0. All right, that people either want to be taller or shorter, but they're providing on average a number that's significantly different from 0. It's either significantly positive or it's significantly negative. All right, so when we do this test, we're going to do a one-way t-test, and we're going to ask, is the mean of this new variable different than 0? To do this one-way t-test, we go to Analyze, Compare Means, One Sample t-test. The mean, the variable whose mean we're going to calculate is this height change variable. And we want to know, SPSS always puts 0 in this box down here, but for once we really do want to know, is the mean different than 0? So we're going to leave that 0 in the box right there, and we're going to click OK. All right, our sample statistic, on average, people in our sample wanted to be 1.34, sorry, I messed up, 5'1" inches taller. And the question is that number significantly different from 0, or do we think it's reflecting chance and sampling error? To find out, we scroll down to our t statistic, which is 2.762, and our p-value, which is 0.006. All right, looking at our decision rules, with a p-value of 0.006, we are going to reject the null. And so we are going to conclude that the mean of this new variable is not 0. All right, it's statistically different from 0. And importantly, it's significantly positive. All right, and a significantly positive result means that on average, people wish they were taller. All right, and so this is our conclusion in plain English. People wish they were taller. Again, I pointed this out in some other video, now all the videos are running together, but I want to point out here, this result does not tell us that at the population level, people want to be 1 1/3 inches taller. What we have tested here is the mean of this variable equal to 0, or is the mean different from 0? The result of this test tells us the mean is different from 0, right? And specifically that it's positive. So all we can conclude is that people wish they were taller. At the population level, the mean could be 0.1, or it could be 10, all right? And we would get this same result, that the mean is different from 0. We don't know what the population mean is. All we know now from this test is that it is significantly greater than 0. If we wanted to estimate something about the actual population mean, we wanted to determine what do we think the actual number is at the population level, we would have to construct a confidence interval. Right? And we don't focus on those in this class. All right, so we talked about it a little bit under sampling, but it's not something that's going to show up on a test or anything else. But if you wanted to be able to say, I'm 95% confident that at the population level, the true mean of this height change variable is, and then have a specific number, you would have to do a confidence interval. All right, so hopefully what you can start to see as we're working through this is that all of these different statistics are just different tools available to allow us to make inferences about what's happening at the population level. Here, we're asking a very basic question, do people want to be taller or not? And that's what this test asks. It does not tell us at the population level what is the exact mean. We would have to do a different statistical test to estimate that. Okay? Another way that we could answer this same question, if people want to be taller, is we could use a paired samples t-test. All right, so if people were perfectly satisfied with their height, then the mean of their actual height answer would be equal to the mean of their desired height answer, their height choice variable. However, if they wanted to be taller, then the mean of these two variables would be different. Okay, so this question, do people want to be taller? We still have no predictor. So we're working in this column where there's no predictor, but now we're going to look at their answers to 2 survey questions. How tall are you? How tall would you like to be? And we're going to ask, is the answer to this question equal to the answer to this question? So we have 2 outcome variables. How tall are you? How tall would you like to be? And we want to know if all the people in the sample, not dividing them into groups, but just everybody, did they answer these 2 questions in the same way? We have no predictor, 2 continuous outcomes. So we're going to do a paired samples t-test. Okay, in this paired samples t-test, the null and alternative always say, is the mean of question 1 equal to the mean of question 2? Sorry, mean of question 1 equal to the mean of question 2, or are those two means different? All right, so ignoring now our new variable, we can ask in SPSS, analyze, compare means, paired samples t-test. Right, we move over the pair of variables that we're interested in. All right, and I'm going to move them over in the order that we looked at them over here, desired height and actual height. We're going to press OK. That's it. This second line opens, but you don't have to put anything there. We're going to click OK. So in our descriptive statistics, we can see that their mean actual height is 67.03. Their mean desired height is 68.37. If we scroll down, skip this. This says correlation. We're not interested in a correlation. We can't turn that off. We just have to skip it. If we come down here, we see that this says height choice minus actual height. And we see the mean here, 1.345. They're telling us that is the mean difference of this equation. Height choice minus actual height returns on average a mean of 1.345. This number is the same as the mean of that new variable that we created, where we subtracted height choice minus actual height. We come over to look for our t-statistic, we see what should be a familiar t-statistic, 2.762, and a p-value of 0.006. These t-statistics are exactly the same. These p-values are exactly the same. All right, and because p is less than 0.05, we reject the null hypothesis. We conclude that people's actual heights differ from their desired heights, and the specific way that they differ is that people want to be taller. Their desired height is larger than their actual height. I show you this test in 2 ways to help demystify this paired samples t-test, all right? Because I think that the paired samples t-test is one that people just have troubles with. I don't know why this one's so confusing, but it's one that people find really confusing. What is happening behind the scenes in the paired samples t-test? You give SPSS 2 variables. SPSS subtracts those 2 variables from each other. It holds that information in memory. All right, so it doesn't, when you do a paired samples t-test, it does not create that variable in your data set, but it takes the 2 variables, it subtracts them from each other, it finds the mean difference. And then the test is asking, is that mean difference different from 0? Which is exactly the same thing that we did in this one-way t-test after we calculated the variable. All right, so the paired samples t-test is basically creating a new variable, question 1 minus question 2, and then it's asking if that new variable is different on average from 0. All right, and so as a result, we get the same answer between question 1 and question 2. Question 1, we did all the work that SPSS does, but we did it out longhand. All right, we created the new variable and then tested to see if its mean was different from 0. In the paired samples t-test, SPSS does this same work, it just does it behind the scenes. All right, so the paired sample t-test is asking, is the difference between question 1 and question 2 0, or is it some number that's different from 0? All right, however, because we computed that new variable, we can use that new variable down here for number C, letter C. Using the new variable you computed in part A, do men wish for more added height than women? All right, so we learned overall that people wish they were taller, all right, roughly 1 1/3 inches taller. It's possible that we're seeing this difference in the sample because the men want to be much taller, all right, maybe 4 inches taller, and the women are fine with their height. They just want to leave their height alone. Or it's possible that everyone in the sample wants to be the same amount taller. All right, we're seeing this in the sample because everybody wants to be 1 1/3 inches taller. Or we're seeing this in the sample because the women want to be taller and the men want to be the same height or shorter. All right, and so we don't know which of those things is happening. How did the men and women's answers combine to form this mean? So we can find out by doing this analysis. All right, so figuring out what kind of test we do. Do men wish for more added height than women? Is this question asking us to divide our sample into groups? All right, we have men versus women. So we do have a grouping variable. It's a categorical grouping variable. So we're going to do either a chi-square test of independence or an independent samples t-test. And the way that we decide is by looking at what is it about those men and women that we're interested in. right? And specifically, we're interested in how much taller they want to be. So what is their answer to this new variable that we created? This new variable is a continuous variable. So we have a categorical predictor and a continuous outcome. We're going to return to our best friend, the independent samples t-test. All right, so in this independent samples t-test, we're going to go to Analyze, Compare Means, Independent Samples t-test. We are not interested in actual height. We're now interested in this new variable that we made, height change. We want to know if men and women have equal answers when it comes to changing their height. All right, so our null hypothesis for this test is the mean of this height change for men the same as the mean of that variable for the women? And the alternative is that they're different, all right? That one group answered this question in a different way than the other group. All right, so we have height change. We're grouping based on gender, 0 and 1. We can leave that in there. We press OK. All right, so we scroll, look up at our means first. The men on average want to be 1.3529 inches taller, and the women on average want to be 1.3412 inches taller. Before we even look at the t-statistic and the p-value, do you think those numbers are going to be significantly different? All right, I would say no. Those numbers are very close to each other. All right, and so for confirmation of that, we can look for our t-statistic and p-value. Because there was such a small difference in the sample means, we see a very small t-statistic, all right, 0.011. And because we have a very small t-statistic, there is a very good chance we found that result due just to chance and sampling error. So we have a large p-value, 0.991. All right, with a p-value of 0.991, way bigger than 0.05, we're going to fail to reject the null. All right, so we cross out the alternative. We're siding with the null hypothesis. And so we conclude that the mean of this height change variable for the men is equal to the mean of the height change variable for the women at the population level. All right, which means that men and women wish for equal additional height. All right, so everybody wants to be taller. It doesn't matter what your gender is. Everybody wants to be taller and by the same amount. Okay, we're going to leave height. My voice is starting to hurt from talking so much. Teacher problem. All right, we're going to move to this question on the survey that asked about who do you make friends with more easily? All right, people of the same sex, opposite sex, or it doesn't matter what gender someone is. All right, it's easy to make friends with everybody, or maybe you find it difficult to make friends with everybody. All right, so in order to do this analysis, we have to figure out what kind of analysis we're going to do. The first thing we have to ask ourselves is, does this question ask us to divide our sample into groups? All right, and so this says, do men and women make friends easily with the same type of people? All right, so we see we do have two groups of people, men versus women. That is a categorical predictor. So we're going to do one of these two tests. The next thing that we have to figure out, excuse me, I used hand sanitizer and it smells so strong. The next thing that we have to figure out is, what is it about those men and women that we're interested in? And the thing that we're interested in is who they make friends with. All right, and if we look back at our survey, we can see that this was asked, is it easier for you to make friends who are members of the opposite sex or the same sex, or does gender not matter? And people had to circle one of these three options. This is a nominal response scale, which means we have a categorical outcome that we're interested in. So we have a categorical predictor and a categorical outcome. So we're going to do a chi-square test of independence. All right, and this chi-square test of independence, if you'll recall, is based on a crosstab table. And so what this is going to look like is we're going to have the answers for the men and the women, and they're going to tell us our three choices here: opposite sex, same sex, both genders. Gender doesn't matter. So we're going to have how many people chose opposite sex, how many people chose same sex, how many people chose both sexes. All right, the specific sex doesn't matter. And we're going to fill in this crosstab table, and then we're going to ask, are the men's answers equal to the women's answers? All right, so for this test, we don't have a lot of spare room on this worksheet here. Our null hypothesis is that group 1 equals group 2. All right, so men are equal to women in terms of how they answered this survey question. And the alternative is that men do not equal women. All right, so they answered this question differently. So we're going to do this chi-square test of independence to find out which one of these are more supported. Is the men's pattern of answers equal to the women's pattern of answers, or are those two distributions different from each other? All right, so to get this chi-square test of independence, we have to start with that crosstab table, all right, which is in the descriptive statistics menu. So we're going to go to descriptive statistics, crosstabs. Gender is our predictor, so we'll leave gender in the columns, but we're no longer interested in how many of them have tattoos. Now we want to know who they make friends with. So we're going to put friends in the rows variable. We're going to make sure that chi-square is checked under statistics, and it is. So we'll press continue, and then we press OK. All right, remember, the crosstab table spits out those results in counts, but we want to convert them to proportions, all right, to make it easier and more accurate when we're interpreting that. All right, so I'm getting out my cell phone calculator here. Remember, when we do this conversion to proportions, we take the number inside the cell and divide it by the total for that group. All right, so 15 out of 68 men said that it's easier to make friends with people of the opposite gender. That is 22.05%. Sorry, the writing over here is going to get a little ugly since I drew those ovals. 13 out of 68 men said that it's easier to make friends with other men, people of the same sex. That is 19.11%. And 40 out of 68 men said they make friends with everyone, which is 58.82% of the men. And now we'll do the same thing for the women. All right, 58 out of 137 women said that it's easy to make friends with men, easiest to make friends with men. All right, 16 out of 137 women, or 11.68%, said that it's easiest to make friends with other women. And 63 divided by 137, 45.99% of women said they make friends easily with both genders. All right, so we have this pattern of responses to this question for the men and the pattern of responses to this question for the women. We can see that there are some differences. So in the sample, the women were more likely to say that it's easy to make friends with the opposite gender, and the men looked like they were more likely to say that it's easy to make friends with both genders. The question is, do we think that these differences that we're seeing in our sample reflect something true about the population, where there really are population level differences between men and women? Or do we think that these differences are pretty small, just reflecting a fluke of our specific sample? All right, so they're unique to our sample, but not reflecting anything true about the population. To find out, we have to scroll down. Oh, these stupid lines that don't delete themselves. We have to look down here for our chi-square statistic and our p-value. All right, so our chi-square statistic is 8.515, and our p-value is 0.014. All right, let me erase this so I can get rid of this. With a p-value of 0.014, would we reject or fail to reject the null hypothesis? All right, so p is less than 0.05. So we are going to reject the null hypothesis, and we are going to conclude that the men were different from the women in terms of how they answered this question. You can't just write that in your paper, all right? Men and women are different in terms of who they make friends with, because the reader is then going to ask, how are they different? All right, so you need to really explain what you found here to the reader. And that's why I've provided some lines down here for giving an answer. What you need to do is look at the data provided by your sample and look to see where are the differences. All right, and so the differences seem to be that women are more likely than men to think it's easy to make friends with opposite sex, right? And the men are more likely than the women to say it's easiest with both sexes. All right, so you would write this out in longer hand. I don't want to spend forever in the video just writing sentences. All right, but we see the big differences here are that 42 versus 22%. So there's a big difference here. Women, so this is sort of amusing, women think it's really easy to make friends with men. Men do not think the same thing about making friends with women, but men are more likely to say it's easy to make friends with both genders. Women are apparently indicating it's hard to make friends with other women. or that's not who it's not the easiest to make friends with other women. Okay, last page. We're almost there. Okay, you guys are getting there. You're almost done. We're going to look at this final question on the survey, right? Just to remind ourselves. In evaluating a potential romantic partner, which is more important to you, looks or personality? This was evaluated on a 0 to 9 interval response scale, where low answers mean looks are more important, high answers mean personality is more important, and right at the middle, people are saying that these two things are equally important to them. All right, so the first question, all right, we're going to use a one-way t-test to determine, do people think personality is more important than looks? All right, and so we know we're doing a one-way t-test because this says people, so there's no groups. All right, we have no predictor here. And the thing about those people that we're interested in is how they answered this one interval response scale question. So we have just one continuous outcome. That's a one-way t-test. And we want to know, do people think that personality is more important than looks, right? Or are these things equally important? All right, and we have to figure out what our test value is going to be. Here we're going to have a kind of unusual test value because this is a kind of unusual scale that goes from 0 to 9 instead of 1 to 9. But our midpoint of this scale is 4.5, right? And we talked about the logic of what we're about to do here in the t-test and correlation video that's on YouTube, but I want to reiterate it right now. When we do this one-way t-test, if our mean result is equal to 4.5, that means that at the population level, we think that students think that looks and personality are equally important when they're evaluating members of the opposite sex. However, if our test result is significantly greater than 4.5, that means that people think that personality is at least somewhat more important. All right, it might be a little bit more important. It might be a lot more important. Remember, the test just says at the population level, we think the mean is greater than 4.5. So the population mean could be 5 or 9, we don't know. But if we conclude that the population mean is greater than 4.5, that means that we think people think personality, I didn't spell that right, personality is at least somewhat more important. All right, and this at least somewhat part, this language is referring to the fact that we don't know if the population mean is 5 or 9, so it's at least a little bit more important, all right, because maybe the population mean is just a hair over 4.5, but that means that personality is at least a little bit more important than looks. It could be a lot more important, but it's at least a little bit. If they answer significantly below 4.5, this means that people, either a little bit or a lot, think that looks is more important than personality. All right, so a mean value less than 4.5 would suggest that people think, looks is at least somewhat more important than personality. All right, so we're going to do this one-way t-test to find out, do people think that these two things are equally important? So the mean response to this question is right there at the midpoint. Or is the mean greater than, meaning people think that personality is more important, or less than, meaning looks is more important than 4.5, that midpoint of the scale? All right, so let's return to our question here. Our test value is going to be 4.5, that midpoint of the scale. We're going to ask SPSS, calculate the mean of this looks variable and test to see if that mean is different than the midpoint of the scale, which in this case is 4.5 because it's a weird 0 to 9 scale. If it was a regular 1 to 9 scale, the midpoint would be 5. All right, so to get this one-way t-test, we're going to go to Analyze, Compare Means, One Sample t-test. We're not interested in height change. Now we're interested in this looks variable. All right, how did people answer that question about looks and personality? And we're going to tell SPSS that our test value is 4.5. So SPSS is going to calculate the mean of this variable, and it's going to compare it to the midpoint, 4.5. We click OK. All right, we see that in our sample, the mean is 4.54. Do we think that 4.5 is significantly different than 4.5? 4.54 versus 4.5? Probably not. All right, when we look down here at our t-test, we see the t-statistic is very small because those two numbers are so close to each other, and the p-value is large, 0.687. All right, with a p-value of 0.687, sorry, we didn't write the null and alternative here. The null hypothesis is that the population mean equals 4.5. All right, so we think at the population level that all students are answering right there at the midpoint, or on average are answering at the midpoint. And the alternative is that the mean is not 4.5. So at the population level, on average, people are saying some number that's either in the personality or looks half of the scale. P.687, we're going to fail to reject the null. So reading this, we think at the population level, the mean of this question is 4.5, which means that at the population level, students think that looks and personality are equally important, right? Personality and looks are equally important. How politically correct of them, right? All right, we can dig a little deeper into students' beliefs. We can ask, are there gender differences in the relative importance of personality versus looks? Does this question ask us to divide our sample into groups? Yes, it's asking if there are gender differences. So it's asking us to divide our sample into groups based on gender. That is a categorical predictor. So we're going to do one of these two tests. And the thing that these two genders have answered that we're interested in is this importance of personality versus looks, which is measured on an interval response scale. So that's continuous data. So we have a categorical predictor and a continuous outcome. So we're going to do our best friend, the independent samples t-test. All right, to get this independent samples t-test, we're going to go to Analyze, Compare Means, Independent Samples t-test. We still have gender down here, so that's good. We can just leave gender. We're not interested in their height, their desired heights anymore. Now we're interested in their response on this looks variable. All right, so we put looks into the test variable box. Remember, this is the variable whose mean gets calculated. When we do this test, we are asking, at the population level, is the mean for the men equal to the mean for the women? Or at the population level, do we think that the mean of this interval response variable is different? Okay, so we're going to click OK to find our answer. Looking first at our sample statistics, the mean for the men is 4.99, and the mean for the women is 4.32. All right, remember the higher answers mean that personality is relatively more important than looks. All right, so in our sample, it looks like the men are more likely than the women to say that personality is more important. The question is this difference large enough to convince us that at the population level, this difference really exists between the men and the women? To find out, we scroll across to our T statistic. Our T statistic is 3.162, and our p-value is 0.002. With a p-value of 0.002, we are going to reject the null hypothesis, and we're going to conclude that the means of the men and the women are different. Now, we have to be very careful here. All right, remember I've said multiple times now, we have to make sure that we do not conclude more than what the test is telling us. Now, when I ask, if we were in the classroom, right, if I was not alone in Connor 111 right now, I would ask someone in the classroom to tell me what is the result of this test telling us. And at least one person would say, let me write this out so that we can see here how this is going to matter in a second. Someone would say, men think personality is more important and women think looks are more important. Okay, somebody would raise their hand and say that this was what we should conclude from this test. Let's look at our alternative hypothesis. Sorry, this is hard to say. Our alternative hypothesis says the mean for men is not equal to the mean for women. All right, so this is not the right conclusion. The right conclusion is men think personality is, I'm going to put relatively because it's relative to looks, relatively more important than the women do. All right, this "then the women do" is an important part of this conclusion because our null and alternative hypotheses are comparative statements. Compared to the women, is the men's answer the same? all right? We cannot draw these conclusions which do not make comparative statements. This is a statement just about men. This is a statement just about women. What we've done is a test that compares the men to the women. So the result of this test is, compared to the women, men think that personality is relatively more important. To illustrate this in a numerical sense, because it's gonna come up in our last two things that we have to do. We have this interval response measure, whose data we're looking at. All right, 9 means personality, 0 means looks, 4.5 right here means that they're equal. What we have found is that the women's mean is about right here, and the men's mean is about right here. And what this independent samples t-test is doing is it's asking, are these two means different? All right, is this difference, this space between the women and the men significant? All right, can error explain all of that difference between the men and the women or not? Importantly, while SPSS sees that the women's mean is 4.32 and the men's mean is 4.99, we would have the exact same result to this test if the men's and the women's answers were here or if they were here. All right, so all three of these tests would produce the exact same results if the means were the same amount different, all right, and the standard deviations were the same. All right, so the test is just asking, is the difference between the women and the men different? It doesn't matter where on the scale that difference is. The question is just about the difference between these two numbers. However, for interpreting, this is important, because if we had seen these means in our sample, nobody would have tried to draw this conclusion. All right, because it would make no sense to say, well, the women have this really high mean, but they think that looks are more important. All right, and if we had these means down here, nobody would have drawn this conclusion because it wouldn't make any sense to try to argue that these men think that personality is more important. However, in each of these cases, compared to the women, the men think that personality is more important because the men's mean is significantly higher than the women's mean. All right, so we have to be very careful in this independent samples t-test that when we draw our conclusion includes that comparative statement. Compared to the women, men think that personality is more important. If we want to draw conclusions about each group separately, all right, the way that this does, then we have to test each group separately. Is the women's mean, all right, is the mean for the women equal to 4.5? All right, so is the women's mean significantly different from 4.5? And is the men's mean different from 4.5? All right, and so when we do these two things, these are one-way t-tests. All right, we are taking the mean for one group of people, comparing it against some set number that's meaningful to us, in this case, because it's the midpoint of the scale. And so what we're gonna do in this is we're gonna say, okay, here's the midpoint. Here's the women's mean, this dotted line. Is this difference between the dotted line and the mean, the midpoint, different? And we're going to do the same test for the men. Is the difference between the men's dotted line and that midpoint different? All right, so we're going to do two follow-up one-way t-tests so that instead of making this comparative statement, we can make statements for each individual group. Do men think that personality is more important than looks? Do women think that personality is more important than looks? To do these follow-up one-way t-tests, we have to select only the men and only the women in the sample. So we're going to learn how to do something new in SPSS. We're going to go to data. Almost all the way at the bottom, it says select cases. Cases is just an SPSS word that means people in the data set. So we're going to select some people from the data set. Currently, okay, so we get this big weird menu. We're not looking at almost any of it, just these first two things right here. Currently, all people are selected. So we're looking at all of the people in the data set. We want to look only at some people, all right? So if a condition is satisfied, so we're gonna click that radio button and then click if. And in this menu, it says select people if, and we want to know over here on our worksheet, for men, is personality more important than looks? So we wanna look first at the men. And if we look at our code book, we can see that for the gender variable, 0 equals male. All right, so we're going to tell SPSS, select people if their gender is equal to 0. All right, so SPSS is going to select just the people in the data set who answered 0 to this gender question. We're going to press continue. We can see now it's going to select people if a condition is satisfied, and that condition is that their gender has to be 0. We're going to click OK. In the output, we don't really see that much has happened, but if we look at the screen that contains our data, we can see, if we scroll over to make gender right here, anyone who answered 1, indicating that they're female, they've been crossed out. All right, so SPSS doesn't delete these people from the data set, it just crosses them out, meaning they're going to be ignored in any analysis that we do now that we have done this select cases menu option. So we're going to do this one-way t-test. For this one-way t-test, we're asking, at the population level, do men think that personality and looks are equally important? All right, which would suggest that their mean to that question is 4.5. Or is the mean significantly different from 4.5, meaning that they think that one is more important than the other? All right, we're going to do this one-way t-test, analyze, compare means, one sample t-test. We still want to know, is their mean on this looks variable equal to 4.5? It's just that now we're testing it just for the men. We press OK. All right, so we have that same mean, 4.99, that we saw in the previous number. And now we're testing, is that 4.99 significantly greater than 4.5? We look for our t-statistic, which is 3.174, and our p-value, which is 0.002. All right, p of 0.002, where's my paper? Oh, it's over here. Our decision rules, 0.002 is less than 0.05, so we are going to reject the null hypothesis. We are going to conclude that men did not answer at the midpoint of this scale. All right, 4.99 is greater than the midpoint, so we're concluding that men at the population level are answering somewhere above the midpoint of the scale, which means that for men, personality is at least somewhat more important than looks. All right, so at the population level, men are somewhere in this looks is more important half of the scale. All right, and that's what we're going to conclude here. Now we're going to do the same test for the women. Remember, we found up here the women's mean is 4.32. The question is that women's mean significantly less than 4.5, suggesting that the women think that looks are more important than personality. So we're going to do another one-way t-test, but first we have to select the women. So we're going to go to data, select cases, if, and we're going to change this from if sex equals 0 to if sex equals 1. All right, we're going to press continue and OK. I realize I just did that super fast. So if you're following along, data, select cases. All right, and then that menu where you choose men or women. All right, so now if we go back to our data set, we can see that now the men have been crossed out. So we're going to look just at the women when we do this analysis. We're going to ask for that same one-way t-test again, except now, whoops, that's not what I meant. Analyze, compare means, one sample t-test. We're doing the same test. Is the mean of this variable equal to 4.5? Now it's going to be done just for the women. We press OK. Here we see that 4.32 mean for the women. Is that significantly different from 4.5? We look at our t-statistic, which is negative 1.413. It's negative because 4.32 is a number smaller than 4.5. All right, and we look at our p-value, which is 0.160. With a p-value of 0.160, do we reject or fail to reject our null hypothesis? We didn't even write them. Let's write them real fast. The null is that the women's mean equals 4.5. The alternative is that the women's mean does not equal 4.5. All right, we are going to fail to reject the null because our p-value is greater than 0.05. That means we side with the alternative hypothesis. All right, which means that, you guys, I've been filming this video for so long and now I'm just saying the wrong thing. All right, sorry. We fail to reject the null, which means we side in favor of the null hypothesis. I apologize. I know that me making mistakes does not make this easier for you. The mean for the women equals 4.5 is what our null hypothesis says. So for women, personality and looks are equally important, all right, because that's what that 4.5 means. 4.5 means these two things are equally important to them. All right, so we've done 3 tests. All right, the independent samples t-test, looking to see if men and women are different. And then we did 2 follow-up one-way t-tests. And if we were writing the conclusion of all of this in the paper, I might write something like, men think personality is more important than the women do. Specifically, men think personality is more important than looks, while women think personality and looks are equally important. All right, so we have this richer sort of conclusion that we can draw because we've looked at this data from multiple angles. All right, we learned that in this comparative sense, the men and the women's means were not equal, and specifically the men thought that personality was more important than did the women. And specifically, we found that result because the men think that personality is more important than looks, and the women think that personality and looks are equally important. All right, so we've really fleshed out our understanding of how men and women at Penn State approached this question anyway. All right, whether there's some social desirability bias in there, we'll never know. All right, but we can look anyway at exactly how they answered the questions. All right, one thing I want to say about this worksheet. There is a test here that we learned about that we do not practice in this worksheet. I know. It's just that there's no good thing in here to really look at a correlation for. All right, so it doesn't really make sense to want to know if any of these things increase the same amount. So we don't have a correlation here because none of these continuous variables really make sense as being related to each other. But I'm going to make another video in just a second here where I try to explain the difference between correlation and a paired samples t-test because a lot of students have problems with these two. Right, and so I'm going to make a video that tries to explain that difference a little more clearly with an example, and hopefully that will help you with this correlation versus paired samples t-test. And we do have ways to practice correlation in the student data that is in the slides. Okay, so if you want practice with this, go back to that t-test and correlation video that's in SPSS, download the student practice data set that's on Blackboard, and you can practice doing those correlations and interpreting those correlations that are in the slides. All right, so until the next video, wash your hands. All right, I hope that you guys are doing okay at home. If you have questions, please leave them as comments or email me your questions. All right, and I'll make sure that the answers get to you. At this point, those of you guys watching this video, so I'll just mention it here. At this point, you guys may be working on writing your final paper, maybe, all right, or you might be working on the data analysis plan. I'm not sure when you're gonna watch this video. If you have questions that cannot be answered, all right, by just sending me an email and getting some email back, I will open up some office hours via Zoom, and I'll send you guys, for those of you guys who haven't used Zoom yet, you just go to the Zoom website and create an account, and then I will send you guys a number to join the meeting, and then we can, you know, talk virtually face-to-face to get answers to your questions. Okay, so I'll see you guys next time. Stay inside, keep washing those hands. Hopefully this will be done soon. Bye.